Good afternoon, everyone. I'm Colin Zheng from Harvard. I will be talking about a constructive proof of von Neumann's Min-Max theorem for two-player zero-sum games. This constructive proof has a number of new applications in cryptography and complexity theory. Some of them, indeed, were our original motivation for this work. This is joint work with Salil Vadhan. So the standard Min-Max theorem has a list of applications in complexity and crypto, starting with Nissan's proof of Impliazzo's hardcore theorem, and was later used to, for example, to show that different notions of computational entropies can be equivalent. Was also used to show results in leakage-resilient cryptography. Was used to show that it's impossible to construct black box constructions of succinct non-interactive arguments from falsifiable assumptions, such as the existence of one-way functions, assuming, for example, pseudorandom generators exist. And finally, it was used in my prior work with Vadhan to give a simple construction of pseudorandom generators from arbitrary one-way functions, all using the standard Min-Max theorem. Now, in complexity-based crypto, our typical result begins with some computational assumption. For example, some problem Y is hard for all low complexity algorithms. And try to reach some conclusion that, for example, says system X is secure against all low complexity algorithms. And a typical proof is by reduction proving the contrapositive. In other words, suppose that there exists a low complexity algorithm A that breaks X. We want to show that there exists a low complexity algorithm B that computes Y well. Now, in most of the applications we saw of the Min-Max theorem, the Min-Max theorem comes in the reduction, playing its magic by giving us some object satisfying certain properties that may not be efficiently constructible. And from that object, we then obtain a low complexity algorithm B. Now, since the Min-Max theorem is non-constructive, it gives you some object but doesn't tell you how to construct it. The low complexity algorithm B has to be non-uniform, meaning that it's a Boolean circuit, even if we start with a uniform low complexity algorithm A. In other words, results of this type will have to start from a stronger assumption, a stronger non-uniform computational assumption that some problem Y is hard even for non-uniform algorithms. Now, the natural question to ask is whether we can find some constructive or uniform Min-Max theorem to replace that so that we can start with a weaker uniform computational assumption and reach a uniform conclusion, where uniform conclusion means that the low complexity algorithm A here is uniform. Now, of course, there may be non-uniformity in other parts of reduction that we have to take care of, but in most of the applications we saw, this is doable. It turns out that indeed such a constructive proof of the Min-Max theorem is known due to Frian and Shapiri from the machine learning community. Unfortunately, the result isn't very well known to the crypto community. The technique is the so-called multiplicative weight update from online learning context. Part of the reason that it's not very well known to the crypto community may be that it's not sufficient for many applications we saw earlier. For example, it can be used to deduce a uniform hardcore theorem. I'll explain why it is so later in the talk. On the other hand, Barak, Hart, and Kelly did give a proof of the uniform hardcore theorem using a similar technique due to Wormuth and Herbster. The technique combines multiplicative weight update with an operation called KL projection, which I'll explain later. But the problem here is that their proof is specific to the setting of the hardcore theorem. It's somewhat ad hoc. It's not clear whether the same technique would transfer to the other applications we want to solve. So our contribution is a new uniform min-max theorem that generalizes the result of Freon-Shapiri using the same technique from Erbsen and Wormuth, which is a multiplicative weight update combined with KL projection. Our contribution here is perhaps giving the right abstraction that immediately enables a number of applications in complexity and crypto. So in most of these applications, we will replace the use of the standard min-max theorem with the uniform min-max theorem, and also take care of other parts of non-uniformity that will give us very modular proofs of uniform results that are often with optimal parameters. I'll explain what optimal parameters mean later. So what is a min-max theorem? Consider a game played between a minimizing player and a maximizing player, where each player selects some n-bit binary string, which is called a pure strategy. Now, the players can toss coins. So their strategies are actually arbitrary distributions on n-bit binary strings, which we call mixed strategies. Once the players have chosen their distributions or their mixed strategies, our expected payoff is computed as an expectation of some arbitrary function f applied on their distributions, where f is a function whose inputs are two n-bit binary strings. And the expectation is taken over the distributions they choose. Now, one may think that the goal for the minimizing player is to minimize the payoff, and the maximizing player wants to maximize it. And one may think that if the maximizing player gets to choose his strategy based on the strategy of minimizing player, then the maximizing player might be able to have some advantage, meaning guarantee a higher payoff. The min-max theorem says this is not the case. It doesn't matter whether the maximizing player gets to choose a strategy first or second. The best he can guarantee, the best expected payoff he can guarantee is always the same. So it's equivalently, if for every strategy of the minimizing player, there's a maximizing player's response that guarantees payoff of at least P, then there's a universal strategy W star that guarantees a payoff of at least P for whatever strategy V of the minimizing player. So natural algorithmic task is to compute this W star efficiently. And indeed, we can do it by a polysize circuit. So the non-uniform min-max theorem is exactly the same with the epsilon slackness in the payoff. And W star can be sort of described by a polysize circuit. And the proof of this is very simple. By the min-max theorem, we have some W0 star here that's a good universal strategy, which is a distribution. We then just take polynomially many independent samples from the distribution and let W star here to be the uniform distribution over these samples. Now the next question is whether we can compute W star in uniform polynomial time. Here, of course, we assume that f, the payoff function, is polytime computable. And instead of assuming that for all v there exists some w, it's kind of a for all exists statement, we assume that there's an oracle, we are given an oracle that for all v, the oracle outputs the w that guarantees a good payoff. So pictorially, what we want to do is to design an algorithm R that interacts with the oracle A, where so R sends some distribution V1 as a mixed strategy for the minimizing player and receives a response W1 from the oracle. And the oracle guarantees that its response always guarantees good payoff. And our goal is to have R interact with A after a number of iterations and output some W star that guarantees a good payoff for all V. So naturally, we want to sort of update update our distribution we send to A using previous answers from A. And a natural way to do it is to put more weight on a string X in V2, where the previous response W1 did not do very well, and put less weight on those where the previous response has done very well. Friand and Shapiri shows that indeed, if we take V1 to be a uniform distribution and we do some operation called multiplicative update here, then we can indeed guarantee that W star, we can just take W star to be the uniform distribution over all these responses we get from the oracle. And that's going to be a good universal strategy satisfying this condition. So just to restate more formally, they give Friand Shapiri give a Pauli n 1 over epsilon time algorithm R that whenever given an oracle A that always finds some Wi with good payoff, then R will be able to output some W star that outputs W star that has almost as good payoff as P for every strategy of the minimizing player. Here, we represent the input to the oracle A as a circuit computing the mass function of the VI, or actually a scalar multiple of the mass function of VI. Now, unfortunately, this is not enough for many applications, as we saw. For example, so basically, in many applications, the minimizing players' mixed strategies cannot just be arbitrary distributions. They have to be distributions that lie in a convex set of distributions. Say, their mixed strategies have to be high entropy distributions. Here's just some examples where we do need this kind of slightly more general games. Now, in such more general games, the min-max theorem still holds. We simply change the quantification over V such that it's always contained in a convex set. And likewise, the non-uniform min-max theorem also still holds. Unfortunately, the uniform min-max theorem of Friand and Shapiri fails. And what we are doing in this work is to give a uniform min-max theorem that works even for such more general games that are needed in applications in crypto. So let's see where the algorithm of Friand and Shapiri fails. So recall they do this multiplicative update in each iteration. So here, the oracle A we have is only guaranteed to have good payoff if its input lies in the convex set. So this is a convex set. We start with a uniform distribution and keep doing the update. And at some point, it's going outside of the convex set. And at this point, the response of A cannot guarantee us anything. So we sort of have to somehow project Vi plus 1 back to the convex set. So we do an update and a projection state back onto the convex set. It turns out that if we use an operation called KL projection, which is analogous to Euclidean projection, except that instead of trying to minimize Euclidean distance, now we try to minimize KL divergence, which is a notion of distance between distributions. If we do this kind of projection, then we still have that if we just take W star to be a uniform distribution over these responses, Wi, then W star is a good universal strategy for all minimizing player strategies that are in the convex set, V. So here we need to be able to efficiently compute the KL projection. Brock, Hahn, and Kelly show how to do it if V is a set of high mean entropy distributions. my prior work with Vadhan showed how to do it for V being the set of high Shannon entropy distributions. So we get a new theorem which says for all nice V, meaning where a KL projection can be efficiently approximated, there's a Pauli N1/epsilon time algorithm R that whenever given oracle access to some A, that always outputs some WI with good payoff, then our algorithm R is able to output some W star. That's a good universal strategy for everything in the convex set V. There's just a quick comparison with the non-uniform min-max theorem. So suppose we take V, the convex set V, to be a set of all delta dense distributions, where a distribution is delta dense if it's a uniform distribution over a subset that has density delta, or a convex combination of such distributions. Now the non-uniform min-max theorem gives us some optimal, some universal strategy W star with support order log 1/epsilon delta over epsilon square, where this W star is constructed by a probabilistic construction, whereas the uniform min-max theorem gives us a similar W star with a noticeably smaller support, which turns out to be optimal in both delta and epsilon. Here, W star is constructed by our smart online learning algorithm. So the message here is that the uniform min-max theorem is better even in the non-uniform setting, quantitatively better. So this has a number of applications. Using the uniform min-max theorem, we can deduce uniform versions of the hardcore theorem, where we take V to be a set of high mean entropy distributions. It can be used to show uniform versions of dense model theorem for similar choices of V. Also, we can use that to show uniform analog of the Gentian-Wicks result of impossibility of black box construction of snarks from falsifiable assumptions, where V is a set of all pairs XY, the set of all joint distributions XY, where X is fixed and Y is an arbitrarily distributed short string, jointly distributed with X. And finally, it was used in my prior work with Vadhan to give uniform characterizations of uniform computational entropy, where we take V to be, again, the set of joint distributions XY, where X is fixed, Y is short, and in addition, Y has high Shannon entropy condition on X. There are a number of other applications, including deducing results we call regularity theorems for distributions, which I will not mention here. So just a high-level picture of what we are doing this work. So we take a powerful algorithm in machine learning and turn it around to get a powerful reduction for complexity and crypto. And this has many applications we saw, and there are possibly more to come. Thank you very much.
Any quick questions? Okay. I have a quick question if nobody else has. So you said, do you have any applications to machine learning from your?
Actually, no. This is a technique from machine learning.
And given the improvement you have, does it give anything improved?
Yeah, I think the technique is already there in learning. So if there's any applications they would have explored it.
Okay.
Yeah, I don't think there's any.
Okay, thanks.
Sure.
Thanks, speaker again.